All right, we talked about pendulums before. Now we're going to talk about mass on a spring, which you should have saw from the sim that you were to do previously this week. Now, the first thing to talk about with motion on a spring is something called Hooke's law. So when we look at a spring, when it's in rest or equilibrium position, this is what we see. The force that we apply to this spring is going to be equal to the spring constant, which is varied for each spring, multiplied by the distance we compress it. So if we take this spring and move it up half a meter, then that'll be our x. K, on the other hand, is something that we have to discover based on the spring, and all springs have different constants. But this is how we find the force on a spring, and it's called Hooke's law. Now let's look at a mass on a spring, and let's look at some force here. Okay, so what we have here is an air track. So we have air coming in, and what that air does is it provides support. So this little cart is actually elevated above the air cart. Gravity's pulling it down. Now, since this object's definitely not moving in the vertical at all, these two forces are going to be equal. The only force that's holding this object in place is the spring. So that's the only force that we can measure using this analysis. So we pull the spring this way, or the cart this way. The force in the spring's going that way. The farther we pull it, the greater the force is going to be. Equilibrium, no spring force. And then if we start to push in, spring force is going to increase, right? So that's what we try to do, and we try to measure that using a force meter. Now, what we see with the motion here is very similar to what we saw with the pendulum. At equilibrium position is when we are moving zero at our 2 points, at our crest and troughs of our motion. Okay, so that's where we're farthest out or away from the equilibrium position. At equilibrium position, C, right, that's when we're going to be moving the fastest. And just like any kind of motion here we talk about with vibrations, we're going to have damping, and this amount here just is going to sink a little bit lower each time. But velocity highest at equilibrium and lowest when we talk about being at our ends or farthest away from equilibrium. So farther away from equilibrium, we should have no velocity whatsoever. So what does this all mean? Again, going back to what we saw here, let's just look at each of these positions. Position A, where the spring is farthest out, all potential energy, because that's where our velocity is zero. As it starts to come back in at B, now we start to see some kinetic energy because we're speeding up. Once we get to the equilibrium position, all velocity, all kinetic energy. As we start to move away from equilibrium position, our kinetic energy goes down as potential increases until we get to the point where we stop before we head back, and that's where all of our mechanical energy is potential. But the energy moves the same way that we talked about with the pendulum. Now, period of a mass on a spring, you can see by this equation, is here. Very similar to what we talk about with a pendulum, except now, when we talk about mass on a string, the mass and the spring constant are what control the period. So if we have a smaller spring constant, we're going to have a greater period. But if we have a smaller mass, we're going to have a smaller period. Okay? So this is the equation. This is the mass, and this is going to be the spring constant, or K, as we call it. Okay? So this is different than pendulum. Remember, pendulum is 2 pi L over G, where the length of the pendulum is always important. If we talk mass on a spring, the spring constant and the mass of the mass that we're having attached to it are going to make the big difference there. So let's just apply this really fast. We have a mass spring system. We want to see which one has the higher frequency. So we got a spring with a K of 300 and a mass of 200 grams, and then we have a spring with a K of 400 and a mass of 200 grams also. So let's go ahead, and we got M over K, right? So for case A, we come down and we go 2 pi, and we want to look at our mass. Normally when we look at the mass, we'll look at it as grams. 200 over 300. And then we look at case B, It's 2 pi. It's 200 over 400. Now, because they have the same mass has no, but the K is different, right? So if we have a higher spring constant, so if our K is greater, then our T is going to be less. It's an inverse relationship. This goes up, this goes down. So this one, case B, will have a smaller period, okay? But now we're talking about frequency. And as you recall, frequency is 1 over period. So let's just say our period here is a small number, let's say 3, and the period here is 6. Which one's going to have the greater frequency? Well, the small period means that 1 over 3, right? And again, this period is 1 over 6. This will have a greater frequency. So what we expect to see is case B will have a higher frequency because it has the smallest period.